Good morning, good afternoon, good evening, wherever you are in the world. Thank you for joining us today. My name is Sarah Alspaugh, and I am your webinar host coming to you from Cincinnati, Ohio, here in the U.S. I'd like to welcome you to today's webinar, our topic, Optimizing Product Development of Fluid Power Components and Systems. And I'd like to welcome and introduce our speakers today. With us, we have Chad Jackson and David Chadwick. I will tell you a little bit about them and then turn things over. Chad is Chief Analyst and CEO, and as Chief Analyst, Chad leads Lifecycle Insights research and thought leadership programs, attends and speaks at industry events, and reviews emerging technology solutions. As CEO, Chad defines Lifecycle Insights vision and change initiatives. Chad's 25-year career has focused on improving executives' ability to reap value from technology-led innovations. He has surveyed thousands of manufacturers, produced hundreds of research and thought leadership publications, and presented dozens of times domestically and internationally. He imparts an influential, independent, and insightful voice on the industry's transition to smart, connected products. And a little bit about David Chadwick. Dave is a business development manager at Siemens Digital Industry Software and is focused on industry solutions from the Solid Edge portfolio. Dave has over 30 years of application engineering, project management, and marketing experience and has been responsible for many successful product data management implementations in small and medium-sized manufacturing organizations globally. We are very grateful and happy to have both of you here today. I know you have your presentation ready to go, so give me just a moment here and I will turn things over to that.
Thanks for that introduction. I appreciate that. And thanks to Siemens for having me on this webinar today. The development of fluid power systems has some new challenges today, and there's a lot of complexity that engineers have to deal with, and that's what we're going to be talking about today, which I'll share an agenda here in a moment. But first, just to give you a little bit of context, let's talk a little bit about what we do, Lifecycle Insights, and the guidance that we provide. So it's probably pretty clear that product design and development is not getting simpler. It's getting complex, more complex in a lot of different directions. People, process, technology usually is kind of what that falls into. Executives pursue initiatives to change those things, to improve how they operate, to improve the products that they develop, and a lot of other things. Now, if you pursue an initiative and you don't do it in the right way, you can actually end up disrupting yourself. So to help executives avoid that, we conduct a lot of research. We publish a lot of thought leadership and guidance on not only what initiatives are a good fit, but how to adopt them. How do you avoid this disruption? How do you get the value out of those initiatives and go on from there? Okay, so that is us in a nutshell. And now let's talk about fluid power systems a little bit. The complexity, I mentioned rising complexity in a lot of different directions, and that's also very true of fluid power systems. You see these systems in all sorts of different applications. They're almost everywhere today. So you got to be able to develop these systems quickly and easily and address requirements, do it on time. So there's a challenge there, and we're going to dive a little deeper into the industry trends here in a moment. But first off, let's take a look at the agenda. We'll start by looking at the industry dynamics of what's going on with fluid power systems. There are some new trends that affect the difficulty of developing these systems. Then we'll look at costing and quoting. What's involved there? What capabilities do you need in place to do that more efficiently so that you can quote accurately, so you can be competitive, but not take on jobs where you lose money? Then we'll talk about mechanical design and analysis. There's capabilities that you can implement there that will help you. Of course, piping and instrumentation diagrams, that's a key part of any fluid power systems. We'll take a few minutes to dive into that. Then we're going to talk about the digital thread. and why that's important, how it's related to fluid power systems, what are some of the complications that it helps address. And then we'll get into some Q&A later on after Dave Chadwick's session. So with that covered, let's dive into industry dynamics. Fluid power systems are definitely part of the smart connected products movement, but maybe in a way that's not quite clear. A lot of companies are switching over to this products as a service type of model. It certainly is a new business model, but it requires some new capabilities in terms of what you deliver. Because you want to maximize uptime, and people are paying for that service, you need to make sure that you deliver uptime. And what a lot of companies are doing is they're instrumenting their products, and in this case, a fluid power system, with sensors so that you can track how it's performing, but also, most importantly, you can predict when you're going to run into issues. And you can perform predictive maintenance or predictive service as a way to maximize uptime. You don't wait until it breaks. You're out there actually ahead of it and actually fixing it. Next up, there's this thing where there are lots of local competitors that are popping up in different regions around the world, and there are different needs in those different regions around the world. So they're serving those needs and actually complying with local regulations, and kind of offering a local type of solution. The larger companies, the global ones, you got to adapt to that. You got to be able to react to that. You have to offer the same level of service and compliance in each of those regions. So that is certainly making it more difficult. The last thing is energy efficiency. People are looking to lower the operational cost of these fluid power systems, and that means for pumps and the flow through the fluid power systems needs to be more efficient so that you can bring the cost down. And that's compelling, both from a perspective of, hey, we're developing a pump and we deliver that for a sale, right? Because it's more competitive, it's attractive because it has a lower cost of operation, but also, if you're offering a product as a service, if you can lower the ongoing operational costs, that means that the service is going to be more profitable. So these are three of the big trends that are affecting fluid power systems today. So what's the takeaway here? Well, the industry is changing. It's advancing. You're seeing new and modern technologies being incorporated into these fluid power systems. And that's a competitive differentiator. But it's also requiring manufacturers and system providers to actually take on new competencies. If you're talking about connectivity, if you're talking about embedding more electronics and monitoring into these systems, then these are new engineering disciplines in some cases for these companies. And you got to be careful because it changes the profit equation for these systems, both from a ongoing development perspective and also from a requirements perspective. So that's something you really have to be aware of as you move forward. And as a matter of fact, let's talk about costing and quoting next. There's really a fundamental thing you got to figure out when you start costing and quoting systems like this. And when you look at the two extremes, they kind of fall into one camp or the other. So when you overestimate complexity, it means that, or you don't understand the complexity of the system necessarily. Maybe there's some unknowns, either from a requirements perspective or how you're going to fulfill the solution. That means you need to hedge your risk. You see a lot of companies that will hedge their risk by actually increasing the price artificially. You might add a factor of safety here to make sure that If there's any surprises, you're still going to be profitable. Now, the downside of this approach, obviously, is that your price is higher than competitors. And you could very well lose these deals more easily. Now, of course, the other end of the spectrum, you underestimate complexity, and you have issues that you overlook or maybe you don't understand, and you come in with a lower bid. Means you might win the job. However, it also means you very likely will have a profit loss type of project. That means you're not going to be making money. You're going to be losing money on the job when you actually deliver it. So you got to strike the right balance between the two. And really doing that is all about understanding what the requirements are and how you're going to fulfill it. So let's make sure that we really kind of touch on this just a little bit more as a good takeaway. The path to success here is you need to bid accurately, right? And that's how you're going to find the happy medium between these two things. And really, to do that, you have to understand not only what are the requirements, how do you translate what a customer is asking for into the solution that you're going to be proposing. So good understanding here from a technical perspective. And maybe that's based on experience. Maybe that's based on, knowing the customer for a long time. But knowing what your solution is, there you have to strike a little bit of a balance too. You got to not actually design the thing and do all the work. You haven't won the job yet. But you need to do enough that you have a high level of confidence that you can bid within a narrow range so that you kind of strike a balance between the two things. So there are some capabilities that you need to be able to do that. One set of capabilities that you need is requirements management. And this is where you formally not only track what the customer is requesting, but also the breakdown of those high-level requirements into technical ones. Another capability that you need in place is this ability to quickly mock up the design. And again, not do all the detailed design work, but actually be able to mock it up very quickly what the design solution looks like. And then finally, you need to be able to assess, okay, how is this going to be installed? You need to have some insight into what's involved there. The difficulty, the length of time, because of course there are costs associated with that as well. Now, traditionally, the way that a lot of providers of these types of solutions or systems, they really rely a lot on spreadsheets and experience. And that, I think that has worked relatively well up to this point. But I think because of the rising complexity, we've seen a lot of companies really struggle. And you fall into those two categories, right? You're either overestimating the complexity, you're hedging your risk so you have a higher price, or you underestimate it and you end up with a job where you actually lose money instead of make money. So the set of capabilities that are more kind of progressive or novel, that can enable new processes, and finding the right balance between overestimating and underestimating complexity falls in here. So integrated requirements is one of them. So not only be able to define, break down, and track requirements, but actually allocate them to different aspects of the system and how they're going to be fulfilled. Another thing that can have a big impact is automating, both from a 3D modeling perspective and a P&ID perspective. Being able to mock up, again, not do all the detailed design work, but be able to very quickly and easily mock up with some confidence what this design solution is going to look like. And then finally, do a quick analysis of the installation. What's the sequence kind of look like? What's going to be involved? What's the time that it's going to take? And all of that. So let's stop here for a moment and just make sure that we're on the same page. I'm not suggesting that you do the full detailed design work. I've mentioned that a few times. There are some technologies out there that will let you do an accelerated kind of pass through the design, and understanding what requirement is going to be fulfilled with what capability in the design solution, and doing a quick analysis. So again, this is where new people, process, and technologies from an initiative perspective can really help. And this is a really important area, making sure that you win the right jobs where you can be profitable, and not every single one, because there might be jobs out there where they're going to be run at a loss almost exclusively because there's unknown issues that are going to crop up. But if you can assess it early, if you can mock up your design, then you can uncover that, and maybe either steer clear or bid appropriately. All right, so let's move on and talk about mechanical design and analysis of these fluid power systems. Certainly is a lot involved there. So there's a few things to think about here, and they kind of point back to the industry trends. So one is you need to make sure that you have good fluid flow through some of the key components like pumps and things like that. So that's one aspect. Another thing, kind of on a larger scale for the overall system, is energy efficiency. You want to make sure that, we talked about this in the industry trends, that you're fulfilling that. And then, of course, you got to look at structural integrity and analyses. So you got to avoid excitation. That can certainly be an issue with frequency loads and that type of thing. So you got to be aware of that, because that can cause failures, no doubt about it. So the traditional way of doing this, if you're going to try and have an organic shape that has good fluid flow, you avoid cavitation. You might end up trying to use these aesthetic design, industrial design tools, get into advanced surfacing, and there's a lot of effort behind that. And frankly, it may not give you the fine-tuned control that you need. You can also run into a lot of data exchange challenges there. When you talk about energy efficiency, there's a lot of folks out there that use spreadsheets, and I know that has worked maybe well for you so far. But as you get into higher complexity type of systems, that's not going to work as well. And same thing with experience, especially as you start to incorporate more and more technology, especially as you look more at predictive maintenance. How do you design for predictive maintenance? Spreadsheets and experience will only take you so far. So there's a new set of tools in each of these areas that we should talk about, kind of emerging tools. One is using subdivision modeling, where you have it's almost like a cage where you can add more and more controls in specific areas and kind of push and pull and drag. And same thing with direct modeling. That's another great way to get in there and manipulate geometry so that you can improve efficiency through that. And you can validate that using integrated fluid simulation. You can actually look for cavitation, recirculation, and you can avoid that as you intend to. And of course, you can also do structural analyses, look at excitation, look at natural frequencies, and change your design to avoid that. So there are new tools out there to help on this front. Okay, so the main takeaways here are that with rising complexity, you need to have new tools and new capabilities to help you address that. And there are emerging technologies that fit squarely into this space and really can make a difference. So that not only do you do it faster, but you end up with a better design solution that you develop that fulfills all the requirements. And it's more efficient, and all the stuff that we talked about in the industry trends. So this is an area where you can invest in and make a big improvement. Obviously, piping and instrumentation diagrams are pretty core to developing fluid power systems. So we'd be remiss if we didn't touch on this at least. So the key here is that you got to develop this documentation. There's a lot of companies out there today that have kind of two separate solutions for this. So on one hand, they develop the P&ID stuff, deliverables, using a 2D CAD application or diagram application in some cases. May not even be CAD. And then they go to route the runs in the fluid power system using a 3D CAD application. Because that'll give you all sorts of stuff like lengths and weights and surface area and all sorts of stuff like that, especially if you have to paint and things like that. So what you end up having is these two different definitions that can diverge from one another. If you make a change to the diagram, it doesn't necessarily mean it's going to be reflected or that update is going to be made to the 3D model. And when you have diverging definitions like this, you can really get into trouble. This is where you order the wrong parts and you end up with delays, cost overruns, and this can sink a project very quickly. So what some companies are doing is adopting these integrated suites. So you can, either start with the diagram and lay that out, and then you almost get a to-do list when you go to route things in 3D, or vice versa. You start to route things in 3D, and then you have a representation within the P&ID. And the great thing is, a key capability to look for here is the ability to update back and forth. All right, so if you make a change to the diagram, it's reflected in the 3D model, and vice versa. If you make a change in the 3D model, it's reflected in the diagram. So these are some capabilities that should not be underestimated in terms of their importance. Fundamentally, design and engineering is all about iteration and change and exploration and understanding if this option is better than this option. And these tool capabilities where you can synchronize back and forth, you can push changes back and forth, allows you to do that pretty quickly and easily. Now, of course, the other option, that I've seen with some companies is they wait until the very end to do one side of work or the other. Like you get the diagram all done and then wait until it's frozen. Okay, this is what it's going to be. Now let's go route things. And you can understand how there's a problem there, right? If you wait to route and then you really don't know what your material costs are going to be, you may not even understand how long it's going to take to install. So it's important to be able to go back and forth, to be able to switch back and forth and push these changes back and forth. So we just talked about the how the nature of design is all about iteration and change, and that's very true of fluid power systems. And what that does is it creates what you see on the screen, which is a digital thread. So let's walk through that. So all the way on the left-hand side, you start with requirements, and then you use that to create different designs, different analyses, and other deliverables. In this case, it's the internal design of a pump and all the components that come along with it, and all the tooling that you need to create those components and how you're going to machine it. What you see on the right-hand side at the top, all those individual lines are different deliverables. And the numbers alongside them show you the different versions of those deliverables. But it's also important to understand that these are interrelated deliverables, right? So if you make a change in one, you need to propagate that change down into all sorts of other deliverables, whether they're the individual mechanical component or the tooling or the machining toolpath. Now, what a lot of companies have done over time is they use a lot of different tools, maybe each one unique and capable within that domain. But the problem here is that when you move from one to another, or let's even just say there's a change all the way on the left-hand side that needs to propagate all the way down through this digital thread, you have to manually make that change. You have to manually propagate that change by exchanging data from one to the next. And that can be problematic. Not all translations are clean, and that can cause extra delays in the process. Alternatively, some companies are using one integrated suite of tools to do all this work in progressive steps. And also, when you make changes, you can propagate that change up and down the digital thread. You don't have to worry about a lot of rework or fixing, broken geometry due to translations. It all just works. So as I noted before, pretty much everybody has a digital thread. You just might not be explicitly aware of it. But there is this interconnected nature between deliverables. You need to be able to propagate change from one to the other. But also you need to manage the digital thread. This is very important to make sure that everybody's working off the same up-to-date information. Otherwise, you're working on out-of-date information, making decisions based on it, and that's where you run into change orders, ordering the wrong parts, scrap and reuse. There's all sorts of issues that kind of come out as a result of that. So managing the digital thread is a key component of all of that. So we talked about a number of things during my part of this webinar. We talked about industry trends. We talked about costing and quoting. We talked about mechanical design and analysis. We talked about piping and instrumentation diagrams. And then we talked about the digital thread. So with that, what I'm going to do is hand it over to Dave Chadwick, and he'll take it from here. Thanks.
Thanks, Chad. And it's great to have this opportunity to talk with you today about optimizing product development for manufacturers of fluid power systems and components. There are many technologies and software solutions that enable manufacturers to implement a digital thread for their product development process. Today, we will focus on just a few of these and show you some examples of how manufacturers in this sector are succeeding. These areas include speeding mechanical design, creating intelligent P&ID diagrams and designing complex 3D piping, integrating mechanical and electrical components and wiring, optimizing products using component and system-level simulation tools, and using simple cloud-based tools for collaborating with suppliers and customers. And just before we dive in, when we talk about fluid power systems, these are some of the manufacturing industry segments that we have in mind. Firstly, manufacturers of fluid power systems, including hydraulic and pneumatic systems, pumping systems, air and gas compressors, turbines, and air conditioning systems. This can include some large-scale systems, such as those shown in the top image here. But also, we're including manufacturers of discrete components of fluid power systems, including, for example, cylinders, valves, pumps, and mechanical seals. Some other large-scale products that utilize fluid power systems are agricultural and construction equipment. For example, this loader has 4 hydraulic rams with the associated pumps, lines, and control equipment. And an example of a smaller scale product that includes many of the components of fluid power systems is this low voltage electric pump used in boats and RVs. Even this low cost plastic pump includes a motor, an impeller pump, and a non-return valve. Chad has talked about how everything that manufacturers do throughout the product development lifecycle is interconnected, and the consequent importance of managing requirements and deliverables as a single cohesive whole. He described this as maintaining a digital thread. From a Siemens perspective, we propose that the digital thread is supported by creating a digital twin. This is a detailed 3D digital model of your proposed product that can be used as the basis for all areas of product development, including, for example, managing customer requirements, concept and detailed design, virtual prototyping, simulation, manufacturing, installation, and service. And we will introduce Solid Edge, a portfolio of affordable, easy-to-use software tools from Siemens that address all aspects of the product development process. Solid Edge combines the speed and simplicity of direct modeling with the flexibility and control of parametric design, made possible with synchronous technology. Solid Edge enables digital transformation for startups, small and medium-sized manufacturers, and departments of large enterprises. Diving a bit deeper into the needs of manufacturers of fluid power systems and components, we have identified 12 key product development processes that are critical for success. All of these are supported by and improved by creating a digital twin of the product. These processes start with the ability to visualize new products before they are manufactured, creating attractive photorealistic images and animations to support your sales and marketing efforts, through areas like responding to RFQs, detailed mechanical design, integrating electrical components, analyzing fluid flow, collaborating with suppliers and customers, and creating documentation to support manufacturing, installation, and maintenance. As we have limited time today, we will take a quick look at 5 of these 12 key processes: speeding mechanical design, developing 2D P&ID diagrams and 3D piping, integrating mechanical and electrical components and systems, simulating fluid dynamics, and collaborating with suppliers and customers. Mechanical design is a core process for product development, and there are several CAD solutions that do a good job of creating accurate 3D CAD models of parts and assemblies, and if required, also creating 2D drawings. Solid Edge has unique capabilities, including synchronous technology that helps speed the design process, and that also help you make design changes and reuse existing design data more easily. Let's look at how one of our customers, Calder in the UK, is benefiting from fast and accurate 3D mechanical design. Calder manufactures high-pressure pumping systems that are used on oil platforms in harsh environments like the North Sea.
At Calder, we design, build, supply, and install high-pressure pumping equipment. As we build for the oil and gas and nuclear industries, we're required to meet very stringent safety and reliability parameters.
Solid Edge gives us really clear visibility of the space constraints that we've got. Everything in orange is all designed in frames. We've got certain components such as the lifting eyes that are added into it. We can create the frame and do a stress analysis, and if we find that it's massively overbuilt, it's easy to change using the frame tool. Sheet metal on Solid Edge, in my opinion, is one of the best features on there. It allows you to create a tab and then change the angles really easily.
It's imperative that we ensure that we can access the equipment for maintenance. We're not going to have clashes between different fabrications. Being able to bite down into the design and understand everything that's going on without having to build the 3D picture up in your own head like you would with a 2D drawing really helps.
Using Solid Edge on a day-to-day basis, my favourite thing about it is that it's very compatible. We can use it on Ian's iPad, so when he goes to customers, we can save 3D PDFs from it.
Now that we have Solid Edge, the items are made for us, they arrive on the shop floor, and the assembly process is done without waste.
In Solid Edge, we can see exactly how everything's going to fit, how all the pneumatic lines and all the cooler hoses and everything go in there.
We can present to the customer before he starts building his platform exactly what the machine is going to weigh and how much space it's going to take up.
We use synchronous technology in 2 ways. We use it when we're designing new items, so we can make something fit between 2 existing parts, and we also use it when we import parts from other manufacturers. Synchronous technology allows us to edit our imported data and make changes that would otherwise be impossible or very difficult for us to make. By creating an accurate design, means there's less time wasted on the shop floor. It's going to come in, they're going to be able to bolt it together, and it's done.
One tool that we have available to illustrate the benefits you can achieve using Solid Edge for mechanical design is the Solid Edge ROI calculator. You can search on Solid Edge ROI calculator to access the online tool. Then you can enter parameters about your business and your design team, and then get an illustration of the time you can save for completing design projects and the additional number of design projects you could complete. You can also download an ebook titled The ROI of Solid Edge with Synchronous Technology that details how we can speed your design process. A specific requirement for some manufacturers, especially those designing larger fluid power systems, is the need to create piping and instrumentation diagrams that document the proposed system, and then the ability to design complex piping systems that are routed around equipment in 3D. Solid Edge offers specific modules to support these requirements. These can be used independently, but they are also closely integrated, enabling the 3D piping design to be driven directly from the 2D P&ID diagram. Let's show you how the 2D P&ID solution can be used to drive the 3D piping design solution.
In this short demonstration, we will show how an intelligent P&ID schematic is used to drive the 3D model. When switching from the P&ID to the 3D environment, the to-do list illustrates the changes that need to be implemented in the 3D model based on the updates to the P&ID diagram. 3D parts are placed from the 3D library, and component properties from the P&ID are automatically assigned. Additionally, the information from the P&ID is used to create the pipework. Here, the correct connection points are clearly identified, which makes it easy to define the appropriate 3D pipeline path, ensuring it avoids any clashes with other equipment. Using Solid Edge's express route, the same two ports are selected and a path created between the two connections. The user is presented with quick select options to select the optimum solution for the pipe route. Again, the to-do list makes it easy to assign all the relevant information from the P&ID to the pipeline sketch. During this process, the correct pipe fittings are automatically placed based on the pipe spec. This saves time and reduces the chance for errors. If changes are needed, additional components can be placed onto a pipe route, and then a simple recalculation of the route automatically adjusts the pipes and places any additional flanges and gaskets as required. Once the to-do list is complete, the 3D model is up to date with respect to the P&ID diagram.
Another key area we will look at is integrating mechanical and electrical components and systems. We see that fluid power systems have an increasing amount of electrical components, for example, sensors, transmitters, and power supplies. It is important to integrate these components and their associated wiring circuits quickly and accurately into electromechanical assemblies. Solid Edge has specific modules for the design of electrical wiring circuits and wire harnesses, and the ability to route these wires accurately around the 3D model of your product. After routing, accurate wire lengths are fed back to the wiring schematic software. Analyses are run to check for issues like open and short circuits, and the optimum wire gauges and fuse sizes can be specified. This helps increase the performance and reliability of the products you are designing. It also minimizes the need to create physical prototypes that can be an expensive and time-consuming part of the product development lifecycle. Now let's talk about the ability to simulate and optimize the performance of your fluid power systems and components. Simulation of the behavior of fluid power systems based on the digital twin enables correct decisions to be made early in the design process, decisions that will help you optimize the performance, energy consumption, and reliability of the products you deliver to your customers. Firstly, when looking at individual components of a fluid power system, such as pumps and valves, you can run a computational fluid dynamics analysis directly within your CAD software. SimCenter FlowAFD for Solid Edge enables rapid setup of fluid flow analyses, and the analyses you run are associative to the CAD model. So if, for example, you make a change to the housing of a pump, you can run the analysis again immediately without the need to specify it again. Let's see a short demonstration of component-level CFD analysis. This animation shows the results of a FlowEFD fluid flow analysis. In this example, we have fluid flow being generated by a centrifugal pump, then flowing through a piping run, and constricted by a control valve. The rotating impeller blades in the pump impart energy to the fluid, forcing it radially outwards and increasing its pressure. This is shown by the dots changing color from green to red. The fluid exits the pump through the discharge nozzle and flows through a pipe system with two right-angle bends. We are now using colors to indicate the speed of fluid flow. Red is a higher speed flow. In this example, a control valve is used to regulate the flow. The analysis shows that the control valve creates a higher speed but lower volume flow. We also have a tool to analyze the behavior of fluids across a complete system. This is described as a 1D simulation and is performed by SimCenter FlowMaster. You can actually use the results of a FlowEFD analysis, like the example we showed earlier, as input to FlowMaster. Using FlowMaster, you can perform what-if type analyses on complete systems, understanding quickly how component size and selection and different operating conditions impact system performance. In this short demonstration, we are using FlowMaster to analyze the behavior of a pumping system. The chart shows the pressure and flow volume over time at a specific location in the system. Both steady state and transient studies are possible using FlowMaster. Users can visually monitor variables throughout the system to identify critical issues. And they can explore potential design solutions quickly and cheaply based on this digital twin of a fluid power system. The final key process that we will touch on today is collaboration with customers and suppliers. The ability to collaborate effectively is increasingly important. We see that traditional supply chains for manufacturers of fluid power systems are under pressure from an uncertain environment around tariffs and from global health concerns. Manufacturers need easy and flexible methods to collaborate with suppliers and customers, both locally and globally. Examples of collaboration can include working with a customer who is in a remote location to review the performance of a component or a system, or working with a tooling manufacturer to investigate an issue you have encountered in your manufacturing process. Siemens has easy-to-use cloud-based collaboration tools that enable you to share design data that was created in many different CAD formats with customers and suppliers. And this can be done in a way that protects the intellectual property of your designs. Let's look at a final example of a manufacturer who is using a digital twin to speed their product development process. Hydrovision in the Netherlands design and manufacture heavy-duty hydraulic winches that are used in the offshore and petrochemical industries. A key challenge for Hydrovision is reacting quickly to their customers' needs. This means that they do not have the time to create physical prototypes. Instead, they design and simulate custom equipment using a digital twin created using Solid Edge. This enables them to optimize their products in the virtual world, ensuring they meet their customers' expectations for the performance and reliability of the hydraulic winches they manufacture.
Hydrovision is very flexible and versatile because we make lots of different products. Hydraulic power packs, winches. We have a service department that refurbishes pumps and motors. We do service on chemical and power plants. And we have special engineers that come and install the equipment at the customer site and make sure it works correctly before he leaves. We have to comply with rules and regulations, especially because we do a lot of offshore things. Our customers mostly offshore and petrochemical firms, so expect quick response and high level of quality and dependability and reliability of our product. And they tell us, well, can you do it in this time? Because we need it by the end of January, tested and installed. There's always a challenge. Technical problems are challenging, but they're fun to solve. It's easy to draw and design in 3D with Solid Edge. The quicker you are, the cheaper you can get, because we can draw quickly with it. We are cheaper and get more orders. Simulation helps us get quick calculations done, so we know in our design stage if parts are strong enough. When I'm almost finished with the 3D product, Luke takes over and makes it into a good model for FEMAP. Where simulation ends, FEMAP goes further.
Some of the objects are too big to make a prototype of it, so it's much too expensive. We trust the program.
There's not much time to make prototypes and invest in that. You have to make the real thing very quickly. The prototypes are made in the virtual world. The first product is the end product. What I see on my screen is really what's going to be there.
And just before we go to the Q&A session, here are a few suggestions on how you can find out more. You can go to our website at solidedge.siemens.com. If you navigate to the Industries section, there is a web page with insights specifically for manufacturers of fluid power systems and components. And you can also download a free trial version of Solid Edge from this website. At this point, I'd like to hand back to our host for the Q&A session.
This concludes today's webinar. Thank you so much for being here, everyone, and have a great rest of your day.